We are delighted to come back to CERIAS this year to continue our journey through technologies that we developed over the last several years. The first one is called Structured Data Folding with Transmutations. It is a secure messaging protocol. And then the second technology that we discussed last year was encrypted user data transit and storage. And it was a complex data structure that basically formed what we called a NUT container. This year, we're going to show you a NUTS ecosystem that uses SDFT and NUTS as a foundational layer to enable this system. And it's an example of a data-centric ecosystem where it's all about the data. And I am Yoon Ao, the inventor of NUTS and SDFT. And I have with us Sotirios Trantafilou, who will actually be operating the demonstrations and showing us how this NUTS ecosystem functions. I'd like to introduce our special guest today, Colonel Robert Banks. Colonel Banks retired from the U.S. Army after a distinguished 37-year career. He previously served as Deputy Director, Current Operations of U.S. Cyber Command. He also served as Chief of Operations of the Army Global Network Operation and Security Center. And he also commanded the largest Army helicopter battalion of 64 Chinooks covering 8 states. And Colonel Banks provided significant contributions at the Joint Staff Cyberspace Division, the National Counterintelligence Security Center, the Army Defense Industrial Base, Electronic Warfare Section in the Asymmetric Warfare Office, National Guard Bureau, and co-chaired the Smart Grid Interoperability Panel while supporting the Tri-County Electric Cooperative. Amongst Colonel Banks' numerous academic degrees, he holds a doctorate in information technology from George Mason University, specializing in hybrid security risk assessment models. He also holds a Bachelor of Science in Industrial Engineering from Texas A&M University, a Master of Science in Engineering Science, Electronic Manufacturing from the University of Texas at Dallas, a Master of Science in Strategic Studies from the U.S. Army War College, and a Master of Science in National Security and Information Protection and Security from the University of New Haven. That's quite a list. On a personal note, it was about 5 years ago that I first met Bob at a cocktail party during DC Cyber Week. Throughout the evening, Bob kept coming back with curiously good questions about nuts. So eventually, we decided to meet for lunch a couple of days later. It was at that lunch that the full weight of Bob's service to the country and expertise in cybersecurity was revealed. And ever since then, it has been my honor to know this patriot who continues to play a part in keeping our country safe. Welcome, Dr. Banks.
Yoon, thank you very much, and truly the privilege is mine to have learned so much from the opportunities as well as the research that I've been doing that has led me in the direction to you. As we talked about, my background is one of curiosity. I'm an industrial engineer. Cybersecurity is not just technology, but the process, the economic incentives which motivate people towards alternative solutions. My Washington cyber opportunity had more attacks in that year than all the previous years combined. My research over several years had led me to focus on cyber economics because I was just unsatisfied with the answers that I had. And my pre-doctoral research uncovered Dr. Parther Pal, which you see his diagram right here. He is a principal scientist at BBN Raytheon, and he talks about the generation of cyber research. And at that time, we were in the third generation, and I was in the big board views of attacks, just tolerating all the attacks. I also got in that research, I got to meet a John Streifert. He was the director of Federal National Resiliency for Continuous Diagnostics Monitoring, which was my role there at Army Cyber. I also met up with Lieutenant Colonel Ron Ross, doctorate at NIST, who led the SPS 853 publications, which is still very prevalent today. In intrusion tolerance, I got to back brief the Lieutenant General 3-star Bob Elder, who stood up Air Force Cyber Command. And he kind of jokingly told him, he says, Bob, I want on your PhD committee because you have the ability to explain highly classified programs in plain language that even I, as a general, could understand why it's important and what the program benefits was. And folks, I was just trying to understand what's going to work, what's not going to work. But that still not satisfied. That has led me towards a philosophical view of the problem, where Ross Anderson defined it as misaligned incentives, information asymmetrics, and externalities. So, okay, how do you measure it? Well, you can look at the volume, the velocity, the variations, the veracity for data at rest, motion, many forms, and data in doubt. Well, at rest, the HP study will tell you that data is doubling. The Verizon reports attackers are successful 80 or 90% of the time, where we only detect 20%. The Semantic Report 2015 showed over 430 million unique malwares, or 2.6 million unique web attacks every day. IBM defines most attacks, even a year later, as unknown. So in my MIT presentations, I asked, what's the equations for these unknowns? Who's writing 2.6 million unique scripts every day? So this led to the current generation of cybersecurity, where MIT's Lincoln Lab staff scientist, Dr. Hammond Okravarva, wrote the survey of the moving target defense, where he's trying to make it difficult for the attackers. They have networks for dynamic host configurations, platforms for rotating servers, virtual servers, runtime where the address space or the layout is randomized. But yet the challenge still comes from the software and the data because of trying to randomize that, you lose the benefit of language standardization. So obfuscations, or making it more difficult, requires more overhead and cost. Dr. Okravarva defines moving target defense as speed, obfuscation, but the challenge of completeness still remains. They are siloed defenses as part of a defense and enterprise subject to the weakest link. While we defend vertically, we communicate horizontally. We need a more complete solution. I think we need to define the 5th generation of security for data security. Examples could be blockchain of a public ledger and proof of the works methodology to support supply chain. Message flow, which uses the data or the business process for the insider threat, and it performs at micro speeds. Now, one of my favorite conversations was on trade policies, because I took a distinguished professor of international trade, Stuart Malware, and General Hayden's construct for a forward-looking way to address the problem, and it gets back to the misaligned incentives of using externalities. But that solution of trade agreements, whatever, it's not going to happen, in anytime soon. So, but there are developments being discussed. There are publications that are coming out, and actually a book of, cyber operations from a legal point of view. So there is development moving, but that takes time. So, but what this leads me towards is this asymmetric anomaly that covers a large patch of data security's overarching needs, for the real market and the developing markets. COVID's businesses now requiring security for increased use of, work at home. Ransomware, where they attack the data security which this type of technology can help rebuild it because you're not centrally located, but you could take advantage of the decentralized nature of the network. You know, this approach is rare because the technologies in terms of the bio-inspired, that's actually quite accurately more than just a marketing slogan. So in terms, I'm very grateful for the opportunity to have learned what this product does, where it's going in direction, because I believe it gets back towards the three questions that Dr. Ross Anderson is saying, you know, in terms of that, the misaligned incentives, the information's asymmetrics, and the externalities. And last, I just want to close that I have bookmarked these presentations, so I intend to partake in many others in the future, because I think your approach, you know, goes beyond just the technologies, but brings in the frameworks that we're currently using, brings in some of the legal concerns. Because again, I do not believe that the challenge in cyber is purely technical. I think that the process and the economics have to be considered. Thank you for your time.
Thank you, Bob, for joining us today and giving us that great overview of the field from your unique vantage point. And now we'll just continue with the rest of the technical demonstration that we were going to show you today.
A simple question is to say, what started all of this? Why did we create NUTS? Why was NUTS necessary in our minds? And some of the questions that led to that are things like, how do I secure the work files on my home PC? How do I email this attachment securely? You know, how do I stop the admin from seeing his pink slip? How do I stop the cloud provider from reading my stuff? What happens to my files in the cloud if they get hacked? How do I recover from ransomware? How do I minimize my email spam? And there's plenty more questions, you know. Why am I always comparing files for the most recent version? If you've ever asked any of these questions on the left-hand box, they lead to various technical terminologies that have been put out in this field of cybersecurity and data management. And some of these are listed here on the right side. And these are very wide-ranging topics and terminologies, and they each have various specializations. It is a complicated question. Our solution to all those questions, or our attempt, is to create a decentralized and distributed system that at the core is all about security and making sharing easy. NUTS is a bio-inspired system, and we propose that DNA is data, and that if DNA is data, then your body and all the cells involved is a data model. And from that, we try to extract the operating principles of that data model and design NUTS around it to kind of mimic that. So what we found out is that when you do this, and you'll see it today, is that the ecosystem actually makes computers work the way you think they should. So when we take a look at what drives the NUTS ecosystem, there are three components to it. At the heart of it is an immutable data container that is secure, and we call that a NUT file or a NUT container. It has one or more payloads, and it can contain anything that you want, whether it's text files, you know, Word documents, spreadsheets, entire databases, or even folders, doesn't really matter, or a file system. And then what we mentioned before is that we put in a lot of metadata that's protected. Some of it is clear text, some of it is not. And these characteristics are extracted from how DNA operates in a DNA data model, and we put that into each NUT separately. So every NUT container, therefore NUT file, has various protected metadata that could help it navigate and kind of enforce and ask to be handled in such a way. And then the third part is the organization of these NUT containers. So we created systems and sets of applications that manage to, deal with these nuts across diverse environments.
There are 4 parties in our demo that is set up as follows. We have Rachel, the real estate agent. We have a buyer and seller named Bob and Sally. And we have a banker named Fred from First Bank. Each virtual machine in this demo has a NUT browser installed. And when you install the NUT browser on a set of your devices, we call this a NUT ecosystem, or you may also hear us using the term eco group. And in this example here, we have 4 eco groups, 1 for each party member. The notebook that runs on your devices in your eco group is actually comprised of 4 underlying applications. The notebook itself, which is a contact, password, and key management system. The NUT browser, which is a user interface for your NUT files. A NUT server, which manages all the local NUT files within your device and your eco group. And the rendezvous server / the NUT router that we discussed earlier, but this is a small local version that decides whether your NUT files need to stay within your eco group or it needs to find other party members and send the file to them. Let's introduce you to the NUT browser. It's your UI to the NUT eco groups. First, you have your quick action buttons at the top for your common functions that you could access. You have your folder navigator on the left, that we call them fogs. They're smart folders that manage smart shortcut links. Here you'll have your workspace. This is where you'll actively be working with your NUT files. To the right of that, you have your metadata window where you can access the metadata of the NUT itself. Below, you have your secure peer-to-peer chat window where you can send secure chat messages. And lastly, on the top, you have your progress bars to show you the encryption-decryption operations of the NUT file. In our first technical example, Rachel and Sally will be exchanging a data file. Here, we will show you the basics of a NUT file and what it means to nutify, how we encrypt data into its portable and secure container. This is the heart of our data-centric design. The ability to securely send the data file in its current form, carrying with it all of its keys and protections, and securely sharing updates back and forth between each person. So our story is going to begin with Rachel, the real estate agent, representing and selling Sally's home. Now, before we dive into the transaction portion of the real estate process, we're going to talk about what a NUT is. So at this point, we've kind of explained in this presentation that we have this container called a NUT, that it's portable, and that we use cryptography to manage the keys and the accesses behind it. So what I want to do here is create something very simple. And what we're going to do is create a file called Somedata. It's just a simple text file. And within this text file, I'm just going to put some type of data in here. So just save. And here now is we have what you would traditionally see is a file that exists on your Windows Explorer or File Explorer, depending on the system that you use. Now, in the world of NUTs, once you import this file into the system, it becomes what we call nutified. And to show you how easy this is, I'm going to pick within my personal management space, I'm going to go to Sally, and I'm going to click on her here. And our options now is you could either simply drag and drop this file into the workspace, or you could right click, select copy, and here now select an open area, a white space within the workspace area, and you'll have an option to paste, and you just go ahead and paste that. And now we're going to start the process of importing the file, applying the encryption on it, and you'll see that end users are able to encrypt their files, have them keyed, and not have to worry about any of the technicalities around it. And that was it. It's been imported into the NUTs ecosystem. Now, again, this is a NUT file, and to look at what it looks like, you'll see that we have our original document, Somedata, And now we have something called Somedatatxtnet, but this is actually a .NET extension. You could tell with the nut icon here. This now is going to live and is going to be a breathing document in the world of the nuts eco group. One thing we could do real quick as well is open this .NET file and see what it looks like. And here you could see where we have its ID. And again, we stamp every nut file with a unique ID. And that is an encrypted document. Opening it up back into the original one, this is what it originally looked like. Now, when we say that it's portable and secure, I could take this document, right-click it, select Share With. I'm going to share this with Sally and hit Apply. It's going to go through the process of applying the encryption that it needs to encrypt it with the appropriate group, and it's going to share it with that group and then send it off over to Sally. And we'll look at Sally's virtual machine in a second. So here we go. Once a document is shared within our nuts ecosystem, it goes from blue to red. So red means that you have a document that's being shared with the outside world, whereas blue means it just resides within your space. Now let's jump over here to Sally. This is Sally. Here we go. Here's the original sum data. And I'm just going to add more data to this file. Save. And I'm going to close this out. So at this point, we've spoken about the ability to import and encrypt the file automatically. We're able to perform a secure file transfer from Rachel to Sally via our group relationship here. Sally now is able to add some content to this encrypted document. And what we're going to do here is we're going to go back to Rachel's machine. And we're going to talk a little bit about secure file and sync sharing as well. So secure file transfer is the ability to securely transfer a file from point A to B. Secure file and sync is what we call it, is our version of collaboration, where you're able to not only securely transfer the file from point A to B, but then points B, C, and so on and so forth could actually make modifications to that file, and that file is propagated and brought back around to all the other members of the groups. That change that Sally would have made would have had two instances of some data. It would have been the original document, and then some data underscore Sally's versions or version 2 or whatever. Again, but we'll get into that a little bit later. Where are the nut files? In this example, we want to point out that the SomeData text file, shown in red, resides only in these two eco groups and nowhere else. This is a distributed system and does not use a central server or store data in the cloud. Its portable, data-centric design does not require traditional third-party services or dependent systems. As you can see here, the file only resides in two eco groups, Rachel's and Sally's.
In our last seminar, we showed you what a nut looks like in diagrammatic form. And on the top left, you see a very simple nut configuration, which is linear in nature. And generally, a nut is a directed acyclic graph structure composed of lock nodes as the nodes itself, and the edges or the connectors are cryptographic links. Now, there's many reasons for this type of structure, but one reason is shown on the right side, where we show you three different nut configurations of different types of lock graphs using lock nodes. And by using these lock nodes in various ways, we could express different security requirements of whatever payload or payloads the nut is supposed to carry. So in the end, the nut is a container that has a complex data structure, and within it, it has sub-data structures called lock nodes. And next, we'll show you exactly what those lock nodes look like at a schematic level. Each nut is a lock graph, and a lock graph is composed of connected lock nodes, and each lock node looks like this. It has 5 major components in this particular data structure, and everything is functioning towards protecting the bag or the payload where you're going to put your data in. Now we have a universal keyhole for every lock node. We have something called a variable lock. There's 3 types of locks in there, which is the OR lock, the secret sharing lock, and the max lock, or otherwise known as the AND lock. And you have something called the stratum access control and the nut access control. And all of these 4 protective layers work together to protect the bag or the payload. So what does Somedatatxtnet look like from our previous demonstration? This is a 7 lock node lock graph, which represents this particular nut file. And it has this configuration where it's connected in a different way. It's nonlinear. It actually has 5 payloads at the right-hand side. And you could tell that in the front, where level 0 is, we have a nut lock. So that's a lock node acting as a gateway. And that is where all the keyholes are defined. And the proper combination of keys will give you certain types of accesses into the various payloads. Now, the payloads themselves, there's 5 of them. The data that we were showing you is actually going into the 3rd payload called the payload block node. And these are protected in various different ways, and we'll go through that in the next slide. You might be asking, what about that structured data folding with transmutation stuff that you mentioned? We went over that last year, as well as I mentioned it in the beginning of this presentation. Well, if you take a look at any of the lock nodes as a data structure, this is where we start using SDFT to enable what we call structured cryptography. And since each lock node has various segments that can lock and unlock data, what we mean by that is it will cryptographically cipher it or decipher it. We need a more systematic, compact, portable, and embeddable method of doing that. And what you're seeing at the top right rectangle is an example of a TAR instruction. So it's a transmutation audit record is what a TAR is. And in this one, it's called B1, NONAC, OB, encrypt, and dyn. So, when we read down that transmutation audit record, press, serialize, encode, compress, S-cipher, digest, and encode, you could almost read the recipe of how that particular payload within this Carnac lock node was actually processed, excluding the key, obviously. And you should be fairly familiar with all of these types of operations. Now, normally, data transformation functions and cryptographic functions are generally not normalized together. Here, transmutations actually normalizes them so that they could be used interchangeably as long as you do operations in a sequence that actually makes sense. So what happens here is that we could now process this payload in this method of pressing it, of serializing it, of encoding it, pressing it, symmetric ciphering it, and then creating a digest, and then base 64 encoding it. We do that that's called the forward mode. Now, when the receiver or we're trying to unlock this lock node, we do the reverse. And that's where the special properties of transmutations come in, is that we've actually mapped the reversible characteristics of any data transformation or transmutation operation that is reversible. Obviously, not all transmutations are reversible, but most of them are. And when they are, we can do it. So the programmer ends up really just worrying about half the instructions, because if you do it right, the other half, which is the reverse process, is guaranteed, right? Now, here's another one. So within the same nut, we actually have a different TAR operating on a different payload. And Similar type of lock node, but in this case, we have something called the nut access control working. And so that requires a different type of locking. And here, the difference is really the size of the AES key, and that we're using actually a 1024-bit RSA key to digitally sign this particular message. And that gives it different properties of control. So this is actually SDFT in action, and you can see the lock node is actually composed of secure messages, and pieces of it can be unlocked and locked at will.
In our next demo, we will cover, with the use of well-known cryptographic techniques, how we can create history for a file and manage its versions, digitally sign it, make it resilient, and even pass URLs privately. We'll use the actors Bob, Rachel, and Fred working to sign a real estate document. To start off is we have a loan document, and Rachel needs to see this loan document. It's already been shared amongst the group, but we're gonna represent this by having a three-way chat. And Rachel's gonna ask them to please send some documents, and of course she's gonna want them to sign them as well. So Bob and Fred are gonna ratify these documents by signing them, and we're gonna do that in two ways. The first way we're gonna do this is Fred here is going to take his loan document, he's going to open it up, and he's going to say Fred's signature. He's going to save this file, and we're going to let replication occur. Now what we're going to go through right now is history and payload versions. So we have the ability to package multiple versions of changes, kind of tying back to the synchronizing and sharing of files. And we're going to demonstrate that here right now. So we're going to go over to Bob here. Here we have three-way chat. Bob has received this message, please send the docs. So obviously he has to go about and make sure that he is signing his docs as well. So here now, Bob is also going to double click on this file. Oops. Now, double click occurred because those replications coming through. Let me save this as well. So this is updating at this point as well. So here we are. We have Fred that signed the document, Bob that has also signed this loan document as well. So here we are. So the upload is completed. The latest payload has been placed in there. Go to Rachel. Let's see where status is with this replicating around. She has version 9. Double click on it. And here we are. We have Bob's signature and Fred's signature in here. Now the cool thing going to history and version control is you could go back, say open, and I could say history and show a previous version of this. Open specific previous version is what I wanted to show, not open previous version. That opens up the previous version. So here you can see all the changes that have been made. Fred signed it, Bob signed it. So here I could select this version here, open it up and say, let me look at it, what it was before Bob touched it. And at that point it was Fred that had signed it, but Bob had not signed the document yet. And you could go and traverse back through the history and the versions of this payload and see all the various versions of this file here and everything that's happened to it. Now that covers payload history and being able to look at different versions. And there's another way you could also sign this document, and that's actually applying a digital signature. Now we could go back here and have Fred say, you know what, everything looks great on my end. What I want to do is just highlight this document here. I'm going to digitally sign it by clicking on digital signatures. Over here, he could find his signature under his, obviously, his password that he needs to access in order to sign it with a certificate. And this now is going to go through the process of actually signing this file itself and securing it and sending it off to the other two people in the group relationship. Select Bob here next. Bob needs to perform the same action. There it is, the loan document came through. You can see now that there's a signature. It's highlighted. I could click on this, and I can see that, again, this is Bob's signature here, that he signed, digitally signed it. And Bob's going to do the same thing. He's going to sign this as well. Enter his password. And it's going to go through the process of signing the nut, performing the encryption operations again, and sending it off to the group. So now Bob has signed this document, digitally signed the document as well. Fred has done the same thing. And while we're working through this, we're going to come back to Rachel, the real estate agent. And we're going to talk about this test file. So we're also going to talk about data resiliency while this process is going through and the documents being passed around. One feature about nuts is its ability to have data resilience, and what that means is that if you illegally tamper with your nut files, we have the ability to bring them back to life and also be able to preserve the data that is in there. So in this example here, I'm going to delete this file illegally from Rachel's desktop. Now this is a file, test file, that was shared with Fred and Bob. So we're going to delete this, and this process takes a little bit longer. So while this action has occurred where I illegally deleted it, we're going to come back and look and check on our loan document at this point. So now it's at version 11. So we want to go and check the signatures here. And here you go. Now Rachel can confirm that there's been 2 digital signatures applied to this document. One is Bob's and one is Fred's. So that has been validated. So now we just showed you that we're able to digitally sign a document as well as do signatures that are embedded within the file, and we could see either the signatures or any changes to the payload file through going through this history. Coming back to our next little demo, it was the illegal deletion of a test file. Now this process takes a little bit longer because what we do is we have a method in which we catalog every single nut file on your system, and what the system does is every so often it walks through all your nut files and verifies its hashes and makes sure that the integrity of the files are correct and they're there. Now in this example here, because I illegally deleted it, what's going to happen is it's going to walk through its catalog. It's going to see that the actual file, the .nut file, is missing, and because it's missing, it's going to say, hey, I need to pull back a copy because a nut file is supposed to exist in this folder structure here. So what it's going to do is it's going to go off to Fred and Bob's ecosystems and say, hey, I've shared a file with you. I need a copy of that file. Can you please send one back over to me? So that is what's currently happening under the hood here. So while that process is in flight, there's one more item that we could go over and talk quickly about. Once Bob has signed and completed his loan documents, he has now purchased the house, and of course, like any other loan, you're going to have to start setting up a portal to log into your bank site to make sure that you can start making your monthly payments. Now, the one thing Fred's going to do here is he has a bookmark, and he set up this bookmark where it's a private URL to their website for Bob to be able to access this portal privately. So he's going to share this with Bob. Hit apply here, and we're going to let this URL go through the process of being shared with just Bob himself. So while that is in flight, we're going to go back and check on Rachel real quick. And here you are. The test file has come back. So I illegally deleted this file. The system said, hey, there's something happened to this data. It's supposed to be there. You didn't tell me about it. You went and fetched it and brought it back. So this is part of what we call data resiliency. And again, the ability to keep your data in place. Think of stuff like ransomware or an insider threat. They may be someone that decided to delete a bunch of files off your machine, or ransomware that may have encrypted that file, you just delete it and the system auto recovers it for you. Now to go back to Bob here, so here we go now to Bob's world, his eco group. Clicks on his relationship with Fred the banker. He sees that Fred shared a private access link with him. So Fred prefers this link to be opened up with Internet Explorer. Now what he's going to do is he's going to double click on this and it's going to take him to this private site. So this is now a private bank site. This is a privately shared URL that Fred sent to Bob. This is a complete random URL at the top here, just to highlight that. So in the world of the internet, you can make this completely private. No one has to see it. You don't have to have him go to firstfederal.com to set up a login site. He could be sent a very private URL. And here I'm going to just go ahead and say, hey, I'm Bob, I'm logging in, and here you go. He's accessing his account online directly with the First Bank. And that completes demo number 3. Where are the nuts? As mentioned in the previous demo, all the files, chats, and URLs reside locally in each actor's eco groups. To recap this demonstration, with history, we can retain all versions of the files, chats, and URLs for provenance and audit trails through the use of our cryptographic techniques. With digital signatures, we can place these into the payloads of a NUT file in a particular version as a signature by one of the actors. Think of it like a confirmation. The use of digital signatures in this example is different, as the traditional use of signatures is used to detect tampering and forgery, which we already covered through our data resiliency example. As you know, data resiliency is a hot topic in cybersecurity. Our secure data-centric container carries with it its history and access control so it can protect itself. Lastly, private portable data structures that are identifiable, like our nuts, can be used in the private URL sharing example. Here with this technique, we could show that instead of having a dedicated public homepage that people need to go to, we were privately sharing this URL with a certain person. Public homepages, as you know, that are dedicated are subject to DDoS attacks and hacking attempts. We can even throw around and entertain the idea and concepts of URL rotations, kind of like key rotations.
When we demonstrate this ecosystem to various audiences, we get a common question, and the question is the NUT router necessary? Some people have suggested that there's stuff that we're keeping in the NUT router that makes the system work, that there's a centralized database somewhere that we're holding all the nuts there, that we may actually be holding keys. And in order to prove that the NUT router is not necessary, we started a little project called Remora. And in this case, what we do is we actually show you that the NUT router is completely unnecessary, and that all the information that's required to make this system work throughout the ecosystem is the source nuts themselves, and that's it. And so fun things happen when source nuts collide, source nuts that have identical IDs collide. And it's how we deal with that collision that makes all of this stuff fascinating, and it actually allows it to work. So here, what we're saying a couple of things here by this example. We're saying that the NUT system is transport agnostic. It is completely independent of any centralized services, including a NUT router, and any mode of transporting nuts will give it its full functionality.
Our Project Remora demo takes us to Rachel and Fred collaborating over a sensitive document. Here, I've selected the Fred from First Bank relationship that Rachel has, and they're collaborating over a time-sensitive document, and there's a denial of service attack that has suddenly started to occur on the cloud provider that hosts their NUT router, or rendezvous server as we also may call it. And from what we've mentioned in previous demos, there's this router that helps you package and send the NUT file from one equal group to another. And in this demonstration here, we're going to show you how we're not dependent on that service at all, and that we could pick any type of medium to transport our NUT file over from one equal group to the next. And in this demo here, we're going to use Gmail. So what I'm going to do first is replicate the outage of your cloud provider by turning off the rendezvous server. Now, this is a cloud hosted rendezvous server. Just to mention, you could also have your own hosted rendezvous server as well, so desired. And you can see up in the upper right hand corner here that it's turned from green to red. So now we have Rachel only using Gmail as an option to communicate this time sensitive document. Now what I'm going to do here is I'm going to double click on it, and we're going to continue collaborating by adding more data. And the NUTbook is still going to go through its process of encrypting the NUT file with its updated payload, packaging it, and wanting to send it off over to Fred. And it's done that, and it's going to find its medium to send it over to. In this case, like we mentioned earlier, rendezvous server's down because of a cloud outage, and we're going to use Gmail instead. I'm going to come over to Fred now. Here's Fred. I'm going to take a look at his Gmail, and here we go. Here's a file that's come in from Rachel. I'm going to click on it, and it's a NUT file. It's encrypted. This file contains all of the access and key management systems that we've discussed in other demonstrations, as well as the payload, file version histories, and all the metadata. I'm going to minimize this here. I'm going to open up his NUTbook, and you can see here that I've already turned off the rendezvous server because there's an outage. And I'm going to double click on this file, and here's add more data. And we're able to use alternative methods such as Gmail or any other cloud provided service or any other email service or any other mechanism, so to speak, of being able to pass data back and forth.
The last feature we'd like to leave you with today is we asked a very simple question. Who said history has to stop at the present? And we call this Project Karnak. Remember, Karnak is Karnak the Magnificent, and it was a Johnny Carson character that sometimes could tell the future. Anyway, we saw the example where you could actually delve into a NUT's history, and you could see the revision versions in the past, and then you could resurrect it if you wanted to and change it over. Well, question begs to be answered is who said history has to stop at the present? That is the conventional thinking, is that history stops at the present. We took it further, and once you change that perception, it becomes where the future is really a calendar, and if you take it into the computer world, that is called, you could put in scheduled events. So we actually see the previous history of revision histories as a continuation of a timeline where you're just standing in the present, and everything behind you are version histories, and that's past, and everything ahead of you is possible future events. Therefore, we gave every NUT a past and a future. This is nuts.
In our Karnak demo, we have a file named taxrecords.txt, as you can see right here. And we're going to do a couple of things here. We're going to go to the metadata, and we're going to select View Event Calendar. And with this file today, what we're going to do is we're going to select the option of deleting it. And this is our 7-year retention policy. So this is something you can set at the corporate level, and this is something that compliance requires to delete. And everyone's pretty much familiar with what that means. So here we could date this sometime in the future. In this example, I'm just going to date it a few minutes ahead, but it could also be dated to be performed 7 years into the future. We're going to select this to apply, and with this applying, take hold. And again, we're applying this metadata to the NUT file itself. And to remind everyone, a NUT file is, because it's portable, that entry carries with that NUT file wherever it goes. So this isn't a setting that is set to activate on the system itself that requires this particular NUTbook application or this particular NUT server. This event is placed in the NUT file, and because of its portability, it could go anywhere that it needs to go and carry it with it. In this example here, I've shared it with Ewan in the group relationship, and he has a copy of this tax record with the exact same retention policy as well. And now here we're going, the time is up. It's going through the process of deactivating this NUT tax record out of the system. This NUT file should no longer exist within the eco group and it's deleted it, and that is Karnak.
The data-centric ecosystem that was demonstrated today can unify your data in a way that very few, if no systems that we know of can do this. And it goes across almost any network, any operating system that could support NUT software, and any hardware. And therefore, your data is everything, and everything else gets commoditized. It's a very, very unique type of technology that we believe shows a different approach to how we think about data, and that once we start thinking about data a little bit differently like this, it starts doing a lot of things on its own with permission. It is data that is intrinsically protected both at rest and in transit in a consistent fashion, and that security is actually portable and under the direct control of each user, where they hold the keys. Where do you store the keys? You store it inside a NUT where it's secure. So the NUT itself kind of gives you that recursive nature, almost like a fractal behavior. And it's a very elegant scheme. And you can see that the benefits are many and the promises are very cool. Here's the familiar reference models from the OSI and the TCP/IP conceptual layers. The OSI has 7 respective layers, and the TCP/IP has 4 of them with their equivalences. What we started realizing when we're working on NUTs is that NUT starts acting as a type of data operating system that sits on a higher layer. So it is a series of applications. Obviously, it uses transport and network layers, but it is where the data is king, and it's the data that's protected from end to end. So it is a little bit more than end-to-end encryption. It is beyond end-to-end encryption. And we started thinking of this as how does it fit in these models? And maybe, we thought, hey, maybe it's time to ask the question whether this model needs to be extended for a ecosystem like the one you just saw today. So this is a good thing to debate on and discuss, but I'd like to leave you with this, and we're open to any questions. And thank you for coming to the seminar today.
Great job. Great presentation. Attendees, if you have questions, you can go ahead and use the Q&A button. It should be located in your Zoom window. Or raise your hand and I can turn on your microphone. Okay, it looks like we have one question from Eric. It says, how does the NUT router make routing decisions?
So that's a very good question. The NUT router obviously has to keep track of IP addresses while there's connectivity, because we have to work through the NAT walls, which still exist for IPv4. We're moving to IPv6, but that's 2 decades in the making. So someday we're going to all get there, but not today. And so the NUT router does make dynamic tables for IP addresses, ports, in order to route it back. But in essence, the main driver of the routing is these NUT IDs. And a NUT ID is a 512-bit SHA-2 hash. It's practically unique. There's no guarantee of uniqueness. But with a 512-bit number, it's large enough to be considered practically unique. And we actually route based upon that. And whatever IPs that you tend to be coming in from any number of computers in your eco group, it'll just map it to that, but really we're just working with NUT IDs.
Okay, we have another one. For Remora, how does the software know what email address to forward the NUT to?
So I think you saw that part where Sotir showed that there's a rendezvous server switch and a Gmail switch. So for the demo, we put in a Gmail thing, and then part of the configuration for that user on that NUT browser is to put in your Gmail address. And also, I think it may require, for you to get an API key from Gmail as well, but also you'd be asked for the login credentials at that point, so that your NUT server running locally in the background can connect to your Gmail API and submit that email on your behalf.
Are there any more questions? Does not look like there are any more coming in, but Yoon, Tira, and Bob, I'd just like to thank you guys for presenting today. Really appreciate it. I think what you're doing here is pretty powerful and pretty amazing, and a very important need. That I can see that a lot of businesses are looking into, and are definitely going to need in the future.
I think one thing that I could leave you with as an overall comment, Mike, is that what we're trying to do in one way is that, companies and systems out there want you to use their resources, their services, and in some way monetize that. Our feeling for one of the motivations of the technology is that we carry in our pockets immense amounts of storage and processing power that doesn't even, we hardly ever use. For the most part, it's idle. And what NUTS Technologies was created for, one of the motivations is to try and make use of your own resources as much as possible, as much as you would like. So think about all the laptops and desktops you have at home that may not be the cutting edge, but is still clearly capable of storing your data in a redundant form, so that we make more efficient use of it and not get charged twice or 3 times for the same space on the cloud drives. Or you get free cloud drives, but the bargain that you strike there is that they get to rifle through all your data for free. So this is a different way that, I started this mainly because I felt a severe frustration with the lack of ability for you to really use your devices and resources to the extent possible, and that they're being underutilized? And why do you want to pay for more? And then why do you want to give away your data that you've carefully collected, and should remain private? And so that's kind of the overall, reasoning behind this. And I think most people who we've spoken to, when you talk about this motivations, they readily agree that it is a problem, but we've almost gotten immune to sort of realizing these are still problems. So I'll leave you guys with that.
Great. Thank you so much. Really appreciate it. And we'll be looking forward to hearing more about this technology and from you too. And hopefully we can have you guys visit us on campus too at Purdue in the future when things start opening back up.
We'd love that, and we're always open to educating, at any point.
Great. Well, you guys take care and stay safe.
All right, thank you.
Thanks. Bye.
Bye.